So this is where we left off last week. We were discussing about min terms and max term. So I'm going to recap from this slide. So in two variables, so we have the truth table, so the possibility of A and B, so going from 0, 0, 0, 1, 1, 0, 1, 1. And then we can write down the min terms, which is the products of the two variables. So the min terms, the first one, we call it M0. So A is 0, so meaning that is the inverse of A. B is 0, again is the inverse of B. And then the min terms is the products of the two. So it is the inverse or A bar and with B bar. And then the max term is the sum of the two variables. So again, the equivalence of the min and the max is that the min is equals to the inverse of the max. So basically, the max is the De Morgan of the min. And then we show a proof of that and how we can prove that the min terms is equals to the max terms. And the proof is down here. So we have the min term, A bar n with B bar. And then we take the inverse of the min term. And then we apply De Morgan. And that shows that it's equals to the max term. And then we also show that the three variables, the min term of the three variables is going from A bar n with B bar and with C bar. And then the max terms is A or B or C. And then the equivalence is the same between the two variables and the three variables. But the three variables will have more min terms because there are three variables, so there are 2 to the nth possibility. And the min terms is associated to what we call the sum of products. So we have all these products here. And if it's on the truth table, if this min terms is true, so meaning that if you have this min terms in our functions, then that min terms will be part of the sum. So it will all with the next min terms that is true. So our functions or Boolean functions will be the sum of all the true min terms on the truth table. And then the max term is what we call the products of sum. So you can see that the max term is the sum. And then the products of sum is that we end all this max term in the truth table. So in this module, we concentrate mainly on the sum of products. So I'm going to discuss this from the perspective of the sum of products. So we mainly talks about the min term. So in 4 variable, the care map. So I've put down the index of the care map. So meaning that if we take A, B, CD as a binary number. So for example, this location here, that will be 0, 0, 1, 0. And the equivalence of that in decimal, that will be the number 2. Okay, so what I have done here, I have listed down all the particular cell on the CAN map with the equivalence binary number of A, B, C, D. And then I showed it down here. Okay, so you go from 0, 1, and then skip 2, 3, and then 4, 5, skip again 6, and then come back 7. And then here, skip a row, and let's go from 8, 9, and then skip columns to 10, and come back 11, and then go back to 12, 13, 14, and then 15. Okay, so if you familiar yourself with this index, it will make your life a lot easier for you to go from the truth table to the CAN map. So you can easily fill the truth table to the CAN map. So that is what we talked about earlier on as the index. But in here, when we talk about the min terms, this number is also referred to the min terms. So for example, 0 here is the min terms m0. And then this term here will be the min terms m sub 10. Or this terms here will be m5. So in our expressions, our Boolean expressions, so if we have, let's say, this is 1, and this is 1 in a very simple expressions. So this function here, f, will be a bar, b bar, c bar, d bar, or with a bar, b bar, and then c, d. And we know that this is the min terms m0, and this is the min terms m3. And what I'm trying to illustrate in this slide, the alternate way of writing the sum of products, you can write f is the sum of these two min terms. So we just writing the locations of these min terms of the CAN map. So this is 0 and 3. So we are summing these two min terms. Okay, so this is a small example that I illustrate here. So extending from that, so this is my CAN map originally. So we have a 1 in a location 0 and 1 in a location 2. And then we have a 1, 12, 13, 14, 15, and 1 at 10. So this is a min terms of M0, min terms of M2, and then here is a min terms of M10, this is M12, M13, M14, M15. So to use these methods of writing our expressions, we can write that if our function is t, t will be the sum of the min term 0, min terms 2, the min terms 8. Okay, I have an m8 here. Okay, so min terms 10, 12, 13, 14, and 15. Okay, so it is the sum of all these min terms, or meaning that these min terms all with these min terms, and then all with these min terms, and so forth. And expand it into this method. of writing. So this is what I show down here. This is actually equivalent. 0 is the min terms of A bar, B bar, C bar, D bar, and then all with A bar, B bar, C, and then D bar, and then and so forth. So you should have 1, 2, 3, 4, 5, 6, 7, 8 min terms in this function. Okay, so this is just going through what I have explained. So I'm not going to go through this again. And the equivalence of the products of sum, or we call it POS. So it is the max term. So the equivalence of these functions, so in a sum of products, so we have 0, 2, 8, 10, 12, and so forth. So we're summing all these min terms. The equivalence of that in the products of sum, it will be the products of the max terms of the missing terms here in the sum of products. So you can see that if I go back to my original, in sum of products, we have a min terms here. The equivalence of that will be a max term, but so in the pos or product of sum, so whenever you have a 0 in the min terms, then you have a 1 in the max term, because this is the inverse of the min terms and the max term, the inverse of each other. So whenever you have a 0 in the min terms, we'll have a max term in the pos or product of sum. So the equivalence of this in the truth table so we'll put M1, 2, M3, and then and so forth. So whenever we have a 0, that's the max terms we want to multiply. So in other words, it will be the missing or the missing terms in our sum of products. So we have here, we have a missing min term, which is 1. And then here we have 3, 4, 5, and 7. That's missing between 2 and 8. So this will be, should I have an 8 here? Okay, so that is the equivalence of the sum of products mapping to the products of sum. And you can show this using De Morgan's theorem. I'm not going to do that here, but you can do it at your own times by applying De Morgan's to the sum of products, and you can show that that will be equivalent to these products of sum. Okay, for example, we have a simple, so we use a simple 2 variables. So we have a function f that has a min terms x bar, y bar. So this is our min terms m0. And then we have all with xy. So min terms of M3. So putting that into our care map, so we got a 1 for this means term M0, and we got a 1 for this means term M3. So in terms of our sum of products or SOP methods of writing, we can write that this expression is equals to the sum of 0, 3. And if we inverse these functions, so we take f bar, and this will be, so whenever we have a 1, it will be 0. Okay, we talk about inversing of functions in the last week's lecture. And when we inverse a functions, whenever we have a 1, we'll make it 0 on the care map. So here our 1 becomes 0, our 0 becomes 1. So if we take the inverse functions and write down their mean terms, so we have m1 plus m2. And if we double inverse these functions, and then we can apply De Morgan's on the inner bar. So we break this bar, and then we change the sign. So we have m1 or m1 bar or with m2 bar. And then the relationship between the mean terms and the max term, we know that the mean terms m1 is equals to the inverse of the max term, capital M1, or capital M1 is equals to the inverse of the mean terms M1. So we can substitute this small m1 bar, which is the mean terms, inverse of the mean terms, and that is equals to the max term. So we show that the inverse of the function f equals to the max term 1, or with the max term 2, and then the whole thing inverse. So that's the inverse function of f. So if we remove the inverse, so means that the function f is equals to the max term 1 and with the max term 2. And this is how we write products. So with the pi sign, so it's a product of the max term 1 and 2. And that's equals to the mean terms m0 and m3. So we show that if we have a missing mean terms in the sum of products, that missing terms will be show up in the max term if we use a products of sum. Okay, so that is another way of proving this relationship. So, but for this 4 variable, you can do the same using the same argument and to show that these two are equivalent. Here is just a simple example using 2 variables to show the relationship between the product of sum and the sum of product. Another terminology that used in digital electronics is the way we express Boolean expressions. So we see that we can express our functions in all the mean terms if you're talking about sum of products. So we write down all the mean terms of the functions. And writing down all the mean terms is what we call the canonical form. Okay, so if it's referred as the canonical form, meaning that the expressions will have all the minterms or the maxterm, depending you are working on sum of products or product of sum. And the canonical form is also known as the standard form. I can go back to some earlier expressions. Okay, so earlier on we used a care map to minimize our functions. Okay, so and then we write down the functions here. So you can see that this functions doesn't contain all the minterms, so it's being minimized. So we can see that here we use a care map and we draw groups of 1, and then we minimize the functions. But if this function were to be in canonical form, so if we take the x as 1, then should have 1, 2, 3, 4, 5, 6 terms in the functions. And each term is a min terms, meaning that each terms here will have the variable a, b, c, and d. But in these functions, the variables in the functions, each of the products term only has 2 variables. Okay, so you have a, c. So in these terms here, b and d is missing. Okay, so this is not in canonical form. This is what we call in minimized form of the functions. So this is just to illustrate the terminology of the words canonical or standard form. If you were told to express your Boolean expressions in canonical form, means that each of the product term must have all the variables. Put down notes here. So if it's a 3 variables, then all the product terms must have A, B, and C in each of the product's term. And that will be in canonical form. Or in other words, from these expressions, you can directly draw up your care map. You can fill in your care map directly from each of these product terms. Whereas in the example that I showed earlier, you can't, or in here. So this is called non-canonical, or is in a minimized form. So the Boolean expression is in the simplest form, or is being minimized. So not all the terms can be found in the expressions. So for example, this expression T here, we have A bar and with C bar, and then O with A bar and with B bar, and then O with B and C. So we can see from these expressions, we have an A variable, B variable, and a C variable. So there are 3 variables in these expressions, but each of the product term doesn't contain all the 3 variables. So if you were to try to draw a care map from these expressions, you can't. So if you have a function like this, in order to draw the care map, you have to go back to your truth table. So you have to write down the truth table of these functions. Only then you can draw the command. Whereas in this function, you don't need your truth table. This itself is already the truth table. You can write down the command directly from these expressions. Okay, I hope you can see the difference between canonical and non-canonical form of expressions. You can also use your Boolean algebra using all the laws we talked about earlier on to expand these functions and make it into a canonical form. Okay, so for example, if I take these terms here, BC, we know that in our Boolean expression law, if it takes A bar or with A, we know that this is equals to 1. So A bar or with A is 1. So means that if I take BC or with 1, it will be the same as itself. So means that if I take the other law, X or with 1 is not N with 1 is also equals to X. So we can do that. So we can take BC and with A bar or with A, because this bracket here is equals to 1. So this is also equals to BC. And then if we expand this out, we have A bar BC or with A BC. So you can see that from the product term BC, it can be expanded into A bar BC or with A BC. And now we have it in our min terms if it's a 3-variable function. Okay, so that is how also you can expand this function from the minimize function into a canonical form. So in order to do that in this particular expressions, you have to do the same for each of these terms. And whenever you have, when you expand it, when you have a term that is duplicate, you can remove that terms or only keep one of them.